EMF and current induced. The long straight wire shown in figure carries constant current I. So this wire carries a constant current I. A metal bar with length capital L is moving at constant velocity v as shown in the figure. So it's moving to the right, maintaining a radial distance from the wire. Point A is a distance d from the wire, so that's the distance between the end of the bar and the wire here. Part A, calculate the EMF induced in the bar. Okay, so this bar is moving with velocity v. This current will create a magnetic field around this wire. And how much will that magnetic field be? Well, first of all, using the right-hand rule, our thumb points in the direction of the current. The four fingers of the right hand curl out of the page on top and into the page at the bottom. So we can see that the magnetic field lines curl like this. So from top to bottom. Okay, so we can write this magnetic field magnitude. This is something we have done many times before using Ampere's law. The magnetic field due to an infinite wire at a radial distance r from the wire is mu 0 I divided by 2 pi times the radial distance r. And if I consider a charge element on this bar, on this conducting bar, this charge element will be subject to a Lorentz force. And what will be that Lorentz force? It's QV cross with B. So any charge element that I pick on this bar will feel a force, dFB, magnetic force, which is equal to dq cross product of velocity with the magnetic field. Now the velocity is to the right, the magnetic field points into the page, and therefore using the right hand rule I can see that my four fingers of the right hand point in the direction of velocity, curl towards the page, the thumb points upward, so that's the direction of the magnetic force. So I see that positive charges will start accumulating on top and the negative charges at the bottom. So positive charges will move towards A and negative charges will move towards B. So let me write this observation. Positive charges will accumulate on top due to the Lorentz force, and negative charges will accumulate at the bottom, so that means they're moving towards B. It's the negative charges moving, actually, leaving behind uncompensated ions. Okay, so the question was, what is the EMF induced? But if I look at part B, it says which point, A or B, is at higher potential. So looking at this, basically, the direction of the Lorentz force, I can conclude in part B. So let me answer part B first. So I will find that there will be a positive potential at A, negative at B. So VA is greater than VB. So I will see point A is at a higher potential. Point A is at a higher potential. Okay. Now, looking at the Lorentz force here that develops on this dq charge element, which is pointing in the from B towards A, and this will create this potential difference between A and B, and there will be an electric field pointing towards B. So positive charges will also feel an electrical force that's going to point down. So the electrical force that they feel, DFE, which is the magnitude of the electric field multiplied by the charge, must be equal to the magnetic force they feel, DFB, which is dq V cross B magnitude when we reach equilibrium. So this is at equilibrium, so that there will be no more motion of charges towards each direction. Okay, and this tells me that the electric field magnitude E here is, because dq's will cancel, electric field magnitude is B times V. The velocity vector and the magnetic field vector are perpendicular to each other, so sine 90 is 1. So this gives me B times V, and electric field magnitude is BV. Now, the EMF induced, which is the potential of A with respect to B, is minus the integral from B to A electric field dot product with displacement. Okay, so going from B to A, electric field dot product with displacement. So this is minus integral B to A. The electric field points in r hat direction. So what is r hat direction? That's this direction from top to bottom. So BV r hat. The displacement is dr in r hat direction, and if we go from bottom to top, that the dr value will be negative, obviously. Okay, so if I perform this integral, I will find minus integral B to A. The magnetic field magnitude is mu 0 I divided by 2 pi r. R hat dot r hat is 1, so V dr. The integral of dr over r will give me natural logarithm. So this will be mu 0 I V divided by 2 pi. Because of the minus sign here, the limits will change. So it's going to be from A to B. So that will be then natural logarithm of R, which is natural logarithm of position of RB divided by RA. The location of RB divided by RA as measured from this straight infinite wire. So first we have evaluated it at RB, and then we have evaluated at RA. So natural logarithm RB minus natural logarithm RA, that gives me this ratio. Now what is RB and what is RA? Well, let's take a look at it. So B, with respect to the straight wire, is at location D plus L, and A is at a distance D. So we can write the induced EMF as epsilon is equal to mu 0 IV over 2 pi natural logarithm RB, which is D plus L divided by RA, which is D. So that's the distance between the long wire and the bar, the straight bar that's moving with velocity v to the right. All right, so let's look at part C of the problem. If the bar is replaced by a rectangular wire of loop of resistance R, what is the magnitude of the current induced in the loop? Okay, so if I look at this situation here, the magnetic field created by this current is pointing into the page inside this loop. But as you can see, since this is an infinite wire, as this loop continues its travel from left to the right, the flux inside this inside this rectangular loop is not changing at all. Okay, so basically I can say that since this is a long wire, and the magnetic field magnitude is mu 0 I divided by 2 pi r, this magnetic field creates a constant flux in the rectangular loop. It's not time dependent. So we see that epsilon, the induced EMF, which is minus the rate of change of magnetic flux, d phi b dt, will be equal to 0. Therefore, if I look at the current induced, the current is the EMF divided by the resistance using Ohm's law. The current induced will be equal to 0. So nothing happens if you have a closed loop like this, and the flux inside the loop is not changing according to Faraday's law. But here there's a motional EMF on this straight bar, because we have the charges on the bar subject to the Lorentz force due to the velocity of the bar and the magnetic field that they are subject to. Okay, so we looked at the EMF and current induced in a straight bar and also a rectangular loop. When they are at a distance d, the closest distance between them is d with respect to this long wire. Since it's a long wire, I'm assuming it's infinite. First, I was asked to calculate the EMF induced in the bar. So what I did was look at the direction of the magnetic field and the force a charge element would feel in this straight bar. A charge element would feel a Lorentz force, which is its charge dq v cross b, and v cross b using the right hand rule gives me the direction of the magnetic force towards the top. So towards point A, that means positive charges accumulate on top, negative charges at the bottom. So potential of A is greater than potential of B. That's the induced EMF direction. Now, at equilibrium, I will see that this Lorentz force will be balanced by the electrical force due to the electric field set up between A and B. So E dq will be equal to dq magnitude of V cross B. So electric field magnitude will be equal to B times V. And since that magnetic field is r dependent, radial distance dependent, mu 0 I over 2 pi r times V is the electric field. Electric field is also radial distance dependent. Dot product with displacement dr in r hat direction. R hat was defined to be with respect to the long straight wire. That's the direction of r. So the potential difference VAB is minus integral b to a e dot dr. So this is VA minus VB that I'm writing. And the minus sign changes the limits here from b to a to b, and that's going to be the integral result, natural logarithm of r evaluated at rb minus evaluated at ra. So that gives me this result, and I notice that rb is L plus D, RA is D. So that gives me the induced EMF. If this is a loop, rectangular loop, because the flux inside the loop is continuous, is a constant as the loop travels with velocity v, because I'm keeping the same radial distance from the wire throughout this travel. Therefore, the induced EMF is zero and the current is zero.